Good morning. Greetings to all. This is Dr. P. Ravindra Kumar, uh, working as a professor in Lakhireddy Balreddy College of Engineering, Department of Mechanical Engineering. So this is the third video. In the last class, we have discussed the macroscopic and microscopic approaches and concept of continuum. So once again recapitulating the important points related to the macroscopic and microscopic approaches. So in a macroscopic approach, few properties are required to describe the state of a matter, and in case of a microscopic, a large number of variables are required to describe the state of a system. And another difference you can find from the macroscope is that it requires a very simple mathematical formula to analyze the system. Simple mathematical formula to analyze the system. Whereas in case of a microscopic approach, it requires a very standard, that is advanced statistical mathematical formula to analyze the system. So the microscopic approach, you can call it as a classical thermodynamics. The microscopic approach, you can call it as a statistical thermodynamics. So that is all about the macroscopic and microscopic. In case of a concept, that is the concept of continuum, what we have discussed is that when you take the 1 meter cubed of a basket, and in 1 meter cubed of a basket, how many air particles are going to be filled up in at atmospheric state condition? When you carry the 1 meter cubed of a basket at higher altitudes, maybe 2 kilometers or 3 kilometers from the ground level, how many air particles are going to occupy at higher altitudes? So that is all about, it is going to discuss this concept of a continuum. So in the concept of continuum, we will treat all the substances. We will treat all the substances as being continuous without considering the action of individual molecules. So the continuum concept is very useful in classical thermodynamics. But at atmospheric pressure, at a ground level, the density, where we will consider the density as 1.2 kg per meter cube. But as we move up, the density goes on decreasing. So that means it indicates that a mean free molecular path of a molecule goes on increasing. So at about 2 kilometers from the ground level, the mean molecular path of the molecule is as large as 3 to 4 meters. So under such circumstances, the fluid cannot be treated as a continuum because the density varies from point to point. And especially in this case, what we have to analyze that the matter cannot be, we cannot analyze the continuum concept in a microscopic study. Especially, the concept of continuum is going to lose its validity when the matter is treated as a microscopically. Say, for example, if you observe the analysis of a ballistic missiles. For example, in the analysis of a ballistic missile, space shuttles, space flights, supersonic rockets, Earth satellites, high vacuum technology, the microscopic point is to be applied over here. So the concept of continuum is not going to be valid under this situation, because here the small volume is there, and in a small volume the mean free molecular path is very large. So in applied thermodynamics, we will adopt largely the macroscopic study of matter. So what you have to understand is that here, that is in case of this one here, the molecular effects. So here the molecular effects, the domain of molecular effects is to be considered over here. Domain of molecular effects is to be considered over here. That means the classical thermodynamics will be applicable up to, that is in this area, the classical thermodynamics. And here, the statistical thermodynamics you have to apply over here. Statistical thermodynamics. Statistical thermodynamics. That means the microscopic point of view analysis is to be applied. So here you observe the volume here. So when the volume is very less, in this case, the molecular effects will be more. So the concept of continuum you cannot apply over here. So this is what you have to observe. So this is all about the continuum concept. Next one is we have to discuss the thermodynamic equilibrium. Thermodynamic equilibrium. In this thermodynamic equilibrium, when there is two terminologies are there, what is the basic difference between a thermodynamic equilibrium and thermal equilibrium? But before that, we need to get some concept related to the steady state and equilibrium point. And the steady state means the properties of a system at any location are independent of a time. At any location are independent of a time. Whereas in equilibrium, the state of equilibrium, that means the properties of a system are uniform and have only one value is assigned to it. And have only one value is assigned to it. Right? So this is the equilibrium, the difference between the equilibrium and steady state. So one is related to the in a time point of view, that is steady state. Equilibrium means uniform value. One value will be assigned to it. Thermal equilibrium. So what is meant by thermal equilibrium? Thermal equilibrium is nothing but a state of a thermal equilibrium, that is a state of a thermal equilibrium. This can be described as one in which the temperature of the system remains uniform. See, observe this. The temperature of the system remains uniform. Observe the location here. The temperature of the system remains uniform. In case of a mechanical equilibrium, so there is no unbalanced force. There is no unbalanced force, or there is no pressure gradient within the system. That is nothing but mechanical equilibrium. What is the chemical equilibrium? Chemical equilibrium is nothing but equality of chemical potential. So that means no chemical spaces, no chemical concentrations should appear before the system and after the system. So if this is okay, then we can consider it as a chemical equilibrium. So this is all about the last class reminding. Now we have to go for the another case. So in this case, so here what we have to study in this particular third video lecture is that so in the third video lecture we have to discuss the uh, state. What is meant by it? So up to now we have discussed this thermodynamic equilibrium. Now we have to discuss the state, property, process, reversible or quasistatic, irreversible process, cycle, causes of irreversibility. So this is what we are going to discuss for today's topic, for today's class. So now here the course outcome from this particular content is that students are going to identify the state of a system, whether whether the state of a system is a change or not. There is a system change is not. System is changing its state or not. Next, the property. What is meant by property? Process, reversible and irreversible process with example. So for today's class, the outcome from this particular content is identifying the state of a system. Uh, that is the intensive property or extensive property. There are the various processes are there, reversible and irreversible process with examples. So this is for today's class. Now come to here. In this case, first thing is um, we need to know when a system is going to undergo the change. So the thermodynamic system undergoes the changes due to the mass and energy interaction. Thermodynamic system undergoes the changes due to the mass and energy interactions. So when these things are happening in your system, there is a system is going to change. System is going to change its state from one property to the another property. So the mode in which the change of the state of a system takes place is termed as a process. The mode in which the change of a state of a system takes place is termed as a process. Say, for example, whether it is carrying out the constant pressure process or constant volume process or constant temperature process. So that is nothing but the process. So any change in the property. So if there is a change in property, say suppose if you take the pressure changes from 1 bar to 20 bar, or temperature changes from 20 degrees centigrade to 40 degrees centigrade. There is a change in state which is going to occur. So the path refers to the series of state changes. The path refers to the series of state changes through which the system passes during the process. Through which the system passes through the changes. So now if you observe the path, that is 1 2 3 4 1. So this is nothing but series of system changes, 1 2 2 to 3 3 to 4 and 4 to 1. So this is nothing but the path, right? Next, the process. So here the mode in which what kind of a process it is taking place. So whether it is a adiabatic process, or it is isothermal process, or polytropic process. So this is the thing. Now here the path refers to the series of state changes. So when a system changes from state 1 to the state 2, this is one path, and the system returns back from state point 2 to the state 1 in this particular path. So the path refers to the series of state changes through which system passes during the process. So this is one kind of a, that is a path, right? This is one path, this is one path, this is one path. But here this is a constant volume process. This is constant pressure process. Again constant volume. This is the constant pressure process. So this is how the changes which are going to get. Now, the cycle, what is meant by cycle? So the cycle refers to the typical sequence of process. The cycle refers to the typical sequence of process, such as a fashion that the initial and final states are identical. The initial and final states are identical. So this is here. Now this is going to be the one cycle. So the reversible cycle. So this is state 1 to the state 2, state 2 to the state 1. So this is nothing but one cycle. It is going to be completed. Next, here this is also one cycle. If you observe this particular diagram sketch. So this is 1 to 2. So one process, 2 to 3, one process, constant pressure process, constant volume process. Again, the system come back to the initial state. That is, this is one. So this is going to complete the cycle. So this you can call it as a cycle, right? So this is the clarity that you have to get. What is the difference between the cycle, path, process, right? So mathematically, it can be said that the cyclic integral of any property in a cycle is 0. So that is the dP is equal to 0, where P is nothing but the thermodynamic property. Now coming back to the property, that is the property can be classified as an intensive property and extensive property. So the intensive property you can also call it as the intrinsic or qualitative property, whereas the extensive property you can call it as the extrinsic or quantitative property. So that means what you have to understand from this particular case is that there are certain properties, certain properties which depend on the size or extent of the system, and there are certain properties which are independent of the size or extent of the system. So if a property depends on to the size of a system, it is nothing but the extensive property, and if the property which is independent of the size of the system, it is nothing but an intensive property. So the properties like mass, volume, weight, enthalpy, entropy, internal energy, which depend on the size of the system, are called extensive property. So the properties like mass, volume, weight, enthalpy, entropy, and internal energy, which depend on the size of the system, are called extensive properties. The properties like pressure, temperature, which are independent of the mass of the system, are called intensive properties. Say for example, pressure, temperature, density, kg per meter cube, specific gravity, and the specific volume, meter cubed per kg, specific volume, meter cube per kg, surface tension, thermal conductivity. So these are all nothing but the intensive properties. So that means independent of mass of the system. So the test for intensive properties to observe that how it is affected when a given system is combined with some fraction or exact replica of itself to create a new system, right? So that is nothing but the intensive property. Then here the ratio of the extensive property to the mass is called as the specific value of that particular property. So that means if you take the specific volume, small v is equal to capital V, this is meter cube per kg. So that is nothing but reciprocal of the density is nothing but specific volume. Specific internal energy, capital U, which is in kilojoules, this small m is in kg, kilojoule per kg. Similarly, the molar properties are defined as the ratio of the properties to the mole number of the substance. Say the capital V meter cube, and this is nothing but the number of moles. So this is nothing but the molar volume and molar internal energy. So capital U divided by N. So this is nothing but molar internal energy. So the ratio of the extensive property to the mass is called as a intensive property, right? So now that here you can observe the properties and how you can classify it as extensive property and intensive property. So if the mass becomes as half in a two partition container and the volume becomes the half, it is nothing but extensive properties. You know, the pressure is same, temperature, density is same, it is nothing but the intensive property in this particular container. Now, what is the basic difference? Differentiate the intensive property and extensive property. The question which is going to, you will get the question like this one. Differentiate intensive property and extensive property. So intensive property is nothing but they are independent of quantity of the system. They depend on to the quantity of a system. In this case, in intensive property, they are independent of the size or extent of the system. But in case of extensive property, they depend upon the size and extent of the system. So the examples already we have discussed related to the intensive and extensive property, right? So hope you have got the property. So property is nothing but a specific value or the characteristic of a observable point that you can call it as a property. Some characteristic, some value has to be mentioned to that particular characteristic of a system, right? So that you can call it as a property, right? So now coming to the quasistatic, that is quasistatic process and non-quasistatic process is there. Quasistatic process and non-quasistatic process. So here, before that one, I need to describe this particular quasistatic process with a diagrammatic sketch. So this diagrammatic sketch, if you observe this diagrammatic sketch, quasistatic process and non-quasistatic process. So in a quasistatic process, when a gas is stored over here, right? And this gas is enclosed by a piston. Gas is enclosed by a piston. And upon the piston, you place some of the incremental weights, say 1 kg, 1 kg, incremental weights up to 10 kg. Say if you go on removing 1 kg by 1 kg, the piston is going to move slowly to the upwards. When you remove 1 kg weight, 1 kg weight progressively, the piston will move progressively upwards. So that means here the properties which are in equilibrium state condition, the properties which are in equilibrium state condition, when you remove the incremental weight, see, observe the point 1, initially it is in the state of a point 1, and slowly if you have removed 1 by 1 slowly, so these are nothing but the equilibrium states of the system. So that means in a quasi-static process, infinitesimally slow process which is occurring, so that all the intermediate states of a system are in thermodynamic equilibrium. Observe that one, thermodynamic equilibrium. All the intermediate states of a system are in thermodynamic equilibrium in a quasi-static process. It is a very infinitely slowly process occurring. In case of a non-quasi-static process, only one single weight of 10 kg is there, and if you remove that 10 kg weight, all of a sudden the piston moves from this position to the top position, and here this is going to come out as a irreversible process, right? So that is a non-quasi-static process. So that means all of a sudden it is going to come back to the initial state. So this is the equilibrium state and this is the non-equilibrium state. So this point you have to understand. Now come here. Uh, uh, the quasi-static process is nothing but infinitely slowness is the characteristic of a process, and all the intermediate changes in states are in equilibrium. Whereas a non-quasi-static process, the nature of a process is very fast. That means, if you remove the 10 kg weight all of a sudden onto the top of a piston, the piston will move from one position to the another position with a speed, with a very fast rate. So equilibrium with intermediate change of a state. Next, the path 1 to 2 of a process can be easily defined due to all the change in states are in equilibrium. Hence, process can be drawn on a graph paper. Onto the non-quasi-static path of a process cannot be easily defined due to the existence of a non-equilibrium change in the state. Hence, this can be drawn on the graph paper with dotted line. See, observe, this is the continuous line and this is the dotted line. So, for a non-quasi-static process, you have to draw it in a dotted line. Next, in a quasi-static process, the processes are reversible in nature. That means it means that it is possible to attain initial state by eliminating the effect. Whereas in case of a non-quasi-static, the processes are irreversible in nature. This is what you have to observe. So it means that it is not possible to attain the initial states by eliminating the effect. Example for the quasi-static process is expansion of gases behind the piston against the infinitely small weights. In case of a non-quasi-static process, expansion of gases behind the piston against a single weight. So the non-equilibrium, that is, this is nothing but the non-quasi-static process. This is nothing but the quasi-static process. So the quasi-static process, you can also call it as a reversible process, and the non-quasi-static process, you can also call it as a irreversible process. So the PV diagram, in this case, the increment, if you remove the incremental weights, so where you can find, so the piston will move slowly, progressively from this particular location to this particular location, and all the intermediate state changes are in thermodynamic equilibrium. Whereas in this case, all of a sudden, removing the 10 kg weight, then the system will come back to the, from state 1 to the state 2, it is following in a dotted line, because thermodynamic, because the intermediate states are in not unequilibrium. Intermediate states are in unequilibrium. This is in equilibrium state condition. So this is all about the quasi-static and non-quasi-static process.